What if the most important photograph in human history looked like a complete failure? We have the first clear images of 3I Atlas, the third interstellar object ever detected, and, well, they show a blur, a smudge that just refuses to focus. But hidden within that haze is a traveler older than Earth, an object moving at the very edge of physics. NASA doesn't want you to see how strange it is, but the truth is coming out. So, what secrets does this blur actually hold? Let's delve into it. Chasing motion. How do you photograph something that refuses to stay still? Capturing 3I Atlas wasn't like shooting an ordinary comet. It moves too fast and shines too faintly for any normal exposure to work. By the time a telescope collects a few seconds of light, the object has already traveled thousands of kilometers, moving at a blistering speed of roughly 12 kilometers per second relative to the sun. A single frame would show nothing but a soft, meaningless streak. To overcome that, as orbital dynamics expert Davide Farnocchia can attest, the telescope had to chase it. Tracking software predicted the comet's path second by second, adjusting the mount in near real time to keep the magnitude 17 object perfectly centered on the sensor. For context, that is over 25,000 times fainter than the faintest star visible to the naked eye. As a result, the stars in the background blurred into trails, but 3I Atlas held its position. What looks like a still blur in the final image is actually motion perfectly cancelled out. The challenge is immense. Even a tiny error in the predicted trajectory would smear the object into invisibility. This wasn't just a photo. It was time made visible, a precise balance between the comet's impossible speed and the telescope's relentless pursuit, a feat of engineering that astronomers at the Minor Planet Center work to perfect daily. Shape without surface. So, what does this interstellar traveler actually look like? Here's where things get strange. In the image, 3I Atlas shows no surface. There is no crisp edge, no solid nucleus shining at its center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself. The elongation is unmistakable. It is not round, and it's not a random smear. It holds a deliberate structure, smooth at one end and uneven at the other. If this were a comet from our own solar system, we would expect a classic teardrop shape with a tail tapering behind it. But 3I Atlas shows a body that seems evenly stretched, almost like a cylinder, with no clear tail direction. This has puzzled every scientist studying it. The shape seems to hint at a rapid rotation, blurring its features together the way a long shutter turns moving water into a flat, silky surface. The team, using methods similar to those pioneered by Karen Meech for Oumuamua, detected a faint brightness variation suggesting a length-to-width ratio of approximately 3:1. This is far less extreme than Oumuamua's 10:1 ratio, but it makes the object's lack of a coma even more baffling. The absence of color. What can a lack of color tell us about an object's past? When astronomers processed the raw images of 3I Atlas, they found something curious: no real color. Most comets show at least a hint of tone, like a greenish halo from cyanogen gas. But this object gives almost nothing. Across visible wavelengths, from 400 to 900 nanometers, its spectrum flattens into a neutral gray. As planetary scientist Alan Fitzsimmons has explained with similar objects, this absence tells us 3I Atlas isn't actively outgassing in any strong way. Instead, we are seeing pure reflection bouncing off a surface so dark it has an albedo or reflectivity of only 2 to 3%, literally blacker than asphalt. Over millions of years drifting between stars, its surface has been bombarded by cosmic rays, baking carbon molecules into complex dark organics called tholins. These materials absorb almost every wavelength of light, combining into a neutral gray when seen from a distance. A slight rise in the infrared spectrum suggests the presence of carbon dioxide ice just below the crust, but the signal is incredibly weak. For an interstellar object, that lack of vibrancy isn't emptiness. It's age, a testament to an eons-long journey through the void. This is the color of endurance. Edge of certainty. How can we be sure this faint smudge is even real? In the raw data, 3I Atlas is barely a whisper above the background noise of space. When you zoom in close enough, the random static of the sky seems louder than the signal itself. But, the difference between noise and a real object comes down to one thing: consistency. Real light behaves with intent. It repeats, it aligns, and it holds a pattern where chaos cannot. across multiple long exposures, the faint streak of 3I Atlas appears in the exact same celestial coordinates. Its brightness curve remains stable despite atmospheric shifts and thermal noise in the camera. That repeatability is the only reason astronomers can call it real. The data achieved a 5 sigma confidence level, the absolute minimum threshold for an official discovery in physics. As astronomer Marco Micheli, who confirmed Oumuamua's strange acceleration, would argue, a persistent signal, no matter how faint, must be treated as a real phenomenon. The final image isn't so much a photograph as it is a mathematical reconstruction, built one photon at a time until millions of calculations reduce the chaos into a fragile, undeniable geometry.
Refusing form.
What happens when your discovery refuses to be discovered? Once the image of 3I Atlas was assembled, it didn't behave like anything the calibration software was designed for. Algorithms that measure coma, nucleus, and tail couldn't settle on a pattern. The numbers diverged. In data terms, that means the target is either unstable or the physics behind it doesn't fit our templates. As interstellar object expert Matthew Knight has noted in his research, these visitors often challenge our models. 3I Atlas breaks the logic. Its confirmed hyperbolic orbit with an eccentricity of roughly 1.1 proves it's not from around here. It behaves like something between 1I Oumuamua, which had no visible coma, and 2I Borisov, which displayed a textbook coma even at 3 astronomical units from the Sun. Its blur is too diffuse to be a solid asteroid but too clean to be an active comet. That ambiguity makes classification nearly impossible using standard cometary models. The picture isn't wrong, it's just showing us a kind of object our instruments and our scientific language weren't built to categorize. It exists in a scientific gray area.
Mathematics of blur.
When an image can't explain itself, you have to trust the numbers. The frame of 3I Atlas is too ambiguous for traditional analysis, so scientists turned to pure mathematics to reveal what the light could not. By plotting its position with micro-arcsecond precision across consecutive nights, they calculated its velocity at roughly 12 kilometers per second relative to the Sun. This confirms a hyperbolic eccentricity of 1.1, the mathematical proof that it's just passing through, moving too fast for our Sun's gravity to ever pull it back. Next, brightness simulations show that if the nucleus is elongated, a slow 11.2-hour tumble could perfectly recreate the uneven brightness we see. Even the blur itself becomes a measurable variable. As orbital dynamicist Davide Farnocchia explains, by deconvolving the image, you can reverse the distortions and find that residual motion smear accounts for about 30% of the elongation, with the rest being the object's actual shape. The image shows uncertainty, but the equations show precisely why it has to look that way.
Distortion or discovery.
Is that a real shape, or just a ghost in the machine? Every astronomical image has them. Cosmic rays can leave small flares, and tiny tracking errors can accumulate and masquerade as structure. When the first image of 3I Atlas was released, that question appeared immediately. How much is the comet, and how much is the instrument? The cylindrical blur could, in part, be a subtle elongation caused by the camera compensating for motion and noise, an effect related to the telescope's point spread function. A residual drift of just half a pixel per exposure when multiplied by dozens of frames creates a false extension. But not all anomalies vanish under scrutiny. As astronomer Wesley Fraser has explored in his work, consistency is key. When the images were independently processed using different software, the same general elongation remained. The angle of tilt and brightness gradient persisted. That argues against coincidence. If distortion were the only cause, its signature would shift between instruments or processing techniques. Instead, the shape repeated itself, asserting its bizarre geometry through the limits of our observation.
Escaping definition.
At some point, the discussion around 3I Atlas stopped being about what it looked like and started being about what it refused to be. It is not a traditional comet, it has no coma or tail. It is not an asteroid, its light curve varies too smoothly to come from a simple rocky surface. The image presents something in between, a blur that resists every attempt at interpretation. Its trajectory confirms an interstellar origin, and paradoxically, that certainty of escape is the only thing about it that feels familiar. The data now paints a picture of pure contradiction, a stable brightness curve suggesting a single body, yet an asymmetry that hints at fragments orbiting a shared center. This object is defined by the fact that no existing model can describe it cleanly. As astronomer Matthew Knight puts it, sometimes an object's most important feature is its refusal to conform to our expectations. This forces us to confront the idea that seeing is not the same as knowing, and our categories are only conveniences, not cosmic truths.
Between categories.
So if it defies every category we have, what could it be? This is where scientific observation meets informed imagination. 3I Atlas sits perfectly between the two prior interstellar visitors. 1I Oumuamua was sharp and fast. 2I Borisov was almost too typical. 3I Atlas is neither, behaving like a memory of both. It's too diffuse to be solid rock, too clean to be a classic comet. It exists in a gap where our definitions fail. It's objects like this that inspire radical new ideas. When data stops fitting patterns, thinkers like Avi Loeb have argued that we must be open to unconventional explanations. While he was referring to Oumuamua, the principle applies here. Is this a new type of dark comet that outgasses materials our instruments can't detect? Could it be a fragment from a tidally disrupted exoplanet, an entirely different class of object? Is it 90% asteroid and 10% comet, or something else entirely? The object is a scientific mystery box. The blur is both evidence and absence, a confirmed detection that withholds its identity, reminding us that our categories are only conveniences, not cosmic truths.
Measured by blur.
When the light from 3I Atlas finally fades from our sensors, this photograph will be all that remains, a faint smear in an archive. In most sciences, such an image would be dismissed for its lack of detail. In astronomy, it becomes the most honest kind of evidence. A blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about this object exists inside that single, unresolved streak: its speed, its path, its rotation, its distance. From this one imperfect shape, entire models of its journey emerge. We don't know what it looks like, but we know what it's doing. Soon, it will leave our system and recede into the same dark it came from, never to be seen again. This blur is not the beginning of a study. It is the end of accessibility. Paul Chodas of NASA's CNEOS has stated that such flybys are fleeting gifts from the galaxy. It's the one clear record of a body from another star crossing through our home, measured by its blur. 3I Atlas is a visitor that escapes our definitions, a blur that exists in the thin space between what we know and what we can only imagine. What do you think is hiding within that faint smear of light? Share your theories in the comments section below. We're always curious to hear what you think. If you want to continue exploring the universe's greatest unsolved puzzles with us, don't forget to like, subscribe, and hit the bell icon so you won't miss our next deep dive. Thank you for watching Stellar Tech.